In 2018, Twitter had been growing immensely for the past 8 years, and its back-end infrastructure was becoming more and more critical to its success. The engineers at Twitter wanted to add TLS support to its cache server to add an extra layer of security to the site. This would prove difficult as the cache server was written entirely in C, forked from two C libraries written over a decade ago. Rather than face the daunting challenge of changing a small part of the existing C library, the Twitter team found that the easiest solution would be to rewrite the entire thing in Rust. There's a common misconception among programmers that writing Rust code is very slow. That is, it takes a lot more time to write a Rust program than it would to write the same program in another language. This is certainly true sometimes, but I would say that in large code bases and most other use cases, the opposite is true. Let's look at an example of when it is slower to write code in Rust. Say we wanted to make a simple greeting function. In C, this program will output the following. Now let's do the same in Rust. These programs are essentially identical, yet the Rust version is giving us an error. Importantly, it is a compiler error, not a runtime error. Here the compiler is complaining that we are using a value after it has been moved. After a bit of headache and some digging around on Stack Overflow, we find a naive solution. Make a copy of the name variable the first time it is used in the greet function, then just use the variable regularly in the second function call. This way the original is preserved and thus unmoved and able to be used again. This code runs perfectly fine, but it's a bit problematic. Most notably, it uses a small amount of extra memory to clone the variable in order to pass it by value to our greet function. As a matter of fact, every additional time we want to greet Cody, we again have to clone the variable, using more memory and tediously taking up more of our time. Surely there must be a better way. After more headache and online searching, we find that there is indeed a proper way to solve this problem. We use references so that our function can borrow the variable without changing it, so we can use it again once the function gives the variable back. This was certainly a lot more work than the C program. We just wanted to print a simple string, and the compiler forced us to answer some tough questions, like whether our function consumes its input or merely references it. And if it consumes it, is that the desired behavior? Do we want to allocate new memory for each consumption, or should we go about this problem a different way? It may seem almost like babysitting, needing to tell the compiler exactly what we are doing at all times. We are, after all, the programmer, and we know exactly what we want to be doing, so why should we be forced to let the compiler know as well? Well, it turns out this becomes extremely important in larger code bases. When working with other people in a team, we don't always know what everyone's intentions are or were. Sometimes when working on a project for so long, we even forget what our own intentions were. Consider the following C code. If I pass a pointer into this function, will its content be modified? And if its content is modified, am I meant to do anything interesting with the new value? Perhaps I need to handle potential error code that is given from the function to the pointer. Or perhaps the potential error code is in the return value, and the pointer stores the result of the function logic. Or maybe neither of these are the case, and the pointer value is read or even written to internally, and we aren't meant to concern ourselves with it. In any case, we don't have nearly enough information just from looking at the function. Of course, this function's purpose was likely crystal clear to the person that wrote it, but to anyone else it is a mystery that will take time and effort to solve. This ambiguity is a core issue that Rust attempts to address. We take the time to tell the compiler exactly what our code is doing so that others in the future will have no difficulty figuring out what is going on. The compiler will tell them what we told it when we had a crystal clear picture of what we wanted. Unsurprisingly, the Rust version of this function is much clearer. Here we can immediately see the purpose of this function. Without even looking at the inner logic, we see that the function returns a result with a success to be discarded, indicated by the empty parentheses, or an error in the form of a string message. The second parameter is passed by value, so we know it will be discarded after the function is called, and the first parameter is a mutable reference, so we know not only that it can be changed, but likely that it will be changed. The person that wrote this function put in extra effort to say that it could. It's worth noting that in a real scenario, it's more likely that both parameters would be passed by value, and the result of the function logic would be passed to the OK result variant. However, I think this example explains things more explicitly. Let's take a look at another example of when Rust saves us time. Our boss comes to us and says we need to make a two-sum algorithm and we need to make it run fast. Multiple critical data paths will depend on the completion of this two-sum algorithm. We initially write our algorithm in Rust, and our code looks something like this. This code looks very similar to any other two-sum implementation, and it was relatively straightforward to write. If we wanted to do the same in C, it would be a bit of a pain importing and learning an external hashmap library that someone wrote for us. But say we did just that. After all, our two-sum needs to be as fast as physically possible. We'll assume the core algorithm is the same for simplicity. When we benchmark the C and Rust versions, we're disappointed to find out that Rust is outperforming C. As it turns out, the random C hashmap we cloned from Cody's GitHub isn't totally optimal, so we decide to switch to C++ to use its built-in hashmap via unordered map, assuming that the performance difference between C and C++ is negligible. Compiling with G++, we find that our Rust program is still faster. But why? After some headache and searching online, we discover that Rust's implementation of the hashmap uses the Swiss hash table, an extremely performant hashmap algorithm developed by Abseil at Google. Martin Ankerl shows an exhaustive set of benchmarks on his website, and when performing 500,000 lookup operations on unsigned integers, he found that the average operation for the Abseil map took 12.6 nanoseconds, while the average operation of the standard unordered map took 54.0 nanoseconds, over 4 times slower. After some headache, documentation reading, and C making, we managed to import the Abseil flat hash map, and our C++ program matches the performance of the Rust program we wrote so long ago. Although all the examples we've seen are just specific cases, they illustrate a pattern of simplicity and rapidity with Rust development. Rust is effortlessly quick because it is a more modern language than C and C++, and thus it is able to have faster default implementations of data structures like hash maps. Rust is clearer syntactically because every variable or function must make the compiler explicitly aware of its purpose. Rust is also completely memory safe, meaning that you will spend more time debugging compiler errors in your favorite editor rather than scratching your head when your program fails at runtime without giving you any indication why, as is the case in C or C++. Code can be written quicker in Rust, meaning more code can be written in Rust and more projects can be finished within a certain deadline. In the case of Twitter, we saw that it was easier to rewrite a decades-old C library entirely in Rust than it was to go through it and figure out how to extend and modify it. C and C++ have dominated the programming industry for the past 40 or 50 years, and though both languages' popularities have been declining, they certainly won't be going anywhere anytime soon. That said, there are still people maintaining COBOL code today. Languages like COBOL or C or C++ don't ever die, but they do become obsolete. Before you write your next project in C++, think if instead it's time to learn a language that will last you for the next 50 years. Thanks for watching.